Okie dokie do. Day 9, we march on toward the end of Unit 1. In fact, it won't be long now. We've got 2 lessons left, and then a review, and then a test. The quick note here says quick quiz, and so that will happen tomorrow, actually physically tomorrow. Like if you're watching this at night, it's going to happen tomorrow during our class time, during lesson 9. And that quiz will cover, it'll be 2 questions, one on asymptotes and the other on the intermediate value theorem. And I'll have already driven that home by the time you read or listen to this. So there you go. So that's our look-see at where we're going. All right, on today's show, we've got to deal with the definition of derivative. The definition of derivative. There's actually 2 ways to define a derivative. And so I would like to give you both the definition of derivative. One definition says the derivative of f is f prime with f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. By the way, this is the definition of derivative in general. This is a general definition for a general derivative of a general function. Nothing surprising here. This quantity here is the slope of a secant line. It is this part. Oh, really? Really? It is this part that turns the slope of a secant into the slope of a tangent. We've been doing that for a couple of days now, so we're now formalizing our treatment of that. We're saying the derivative of a function f is the function f prime, and that function f prime is the limit of the slope of a secant line as the change in x gets closer and closer to 0. If we're looking at a specific point and not in general, there are 2 ways to do that. The derivative of the function f at the point x equals a is, well, first of all, we call it f prime at a, and it is the limit as h approaches 0 of f of a plus h minus f of a all over h, or it is the limit as x approaches a of f of x minus f of a over x minus a. And I'll do 2 quick pictures so that you know that what we're really talking about is the same thing. Generic function, whee! And I'll clone that so that it's exactly the same over here. Well, mostly the same. In the case on the left, what we're doing is we're picking a generic point A. We're moving over some distance h, and we take the slope of the secant line and then squeeze that h smaller and smaller and smaller. It's exactly what we do for the definition of derivative in general. We're just applying it at a very specific point A. So again, this part is the slope of a secant line, and the limiting process makes it the slope of a tangent line. Over on the right, we take our generic point A, we move over to some generic point x, and we take the slope of a secant line through those 2 points. Again, This is the slope of a secant line. F of x minus f of a is the change in y. X minus a is the change in x. So the fraction is the slope of a secant line, and we take limit as x approaches a. That squeezes x and a together, turns a secant into a tangent. So for us, big vocabulary word, differentiate. Differentiate means to find the derivative. Anytime you are asked to differentiate, you take the particular function and you find the derivative. I have a couple of examples. One is f of x equals x cubed. The other is g of x equals radical x. I'll walk through them briefly. We'll kind of put them together, and then we're almost set. F of x equals x cubed. So I'm going to use the basic definition of derivative. I'm going to take a limit as x approaches, as h approaches 0 of f of x plus h minus f of x over h. Clearly, we should know by now, if you try to sub 0 in for h, you're going to get 0 on the top and 0 on the bottom, and so that's just bad. And so instead, algebra to the rescue. X plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed. Love the binomial expansion theorem. The x cubeds drop out like you wish you could. Luckily, everybody that's left has an h in him. So we suck. Those h's drop because h is not 0. It gets close to 0, but it is not 0. And so now we say, what happens as h gets closer and closer to 0? The 3x squared is unaffected. 3xh, well, that gets closer and closer to 0. H squared, that gets closer and closer to 0. And so the derivative is 3x squared. Over on the right, I'll use the alternate definition of derivative here. I'll use the alternate definition. I'm going to say f prime. Really? The function is g. Really? Really? I'm going to use g prime of a. I'm going to figure out what g prime of a is, and then because a is generic, I can just throw an x back in when I need to. I'm going to take the limit as x approaches a of g of x minus g of a over x minus a. That's a limit as x approaches a of g of x minus g of a over x minus a. Well, what gets us in trouble here is a radical, and so we get out of trouble with the conjugate. This is familiar to us from our work in previous courses. The conjugate gets us out of trouble. And so what have I got? My denominator is beautiful, and I'll leave it in factored form, so should you. Your numerator, that's x drop drop minus a. X minus a. Those go away, and we're looking for the limit as x approaches a. So that's 1 over 2 radical a. Now, g prime of a is 1 over 2 radical a, so g prime of x is 1 over 2 radical x. It's one of those things that almost makes sense if you think about it. But this is cool. Thought. What if the function is piecewise defined? what if the function is piecewise defined? What if h of x is the function x cubed if x is less than 0 or equal to 0, and radical x if x is greater than 0? What if that happens? Well, the picture looks something like this. Looks something like that. And so that's smooth almost everywhere, and smooth functions have derivatives. If the function is piecewise defined, its derivative is likewise. The derivative of x cubed, we learned from here, is 3x squared. So the derivative on the left side is 3x squared. We know for certain that that will be true less than 0. We do not know if that will be true at 0. Because if the derivative exists at 0, then the derivative coming from the left has to equal the derivative coming from the right, and we don't know if that's true yet. On the blue side, the derivative of radical x was 1 over 2 radical x, and that will be the derivative for x greater than 0. So the question is, what is h prime of 0? Well, if h prime of 0 exists, then the derivative when I substitute 0 here has to equal the derivative when I sub in 0 here. And guess what? They don't. And since they don't, h prime of 0 does not exist. And you can well imagine, coming from the left, if I try to draw a tangent line, it looks something like this. But coming from the right, if I try to draw the tangent line, it looks something like that. And so we can't talk about drawing the tangent line at 0 because we won't know which way to draw it. Okay, you will come to say things like h prime of 0 does not exist because the graph of h has a corner at x equals 0. I'm going to throw this quick side note in. In your textbook, there is an exploration on page 102. And you probably ought to take a look at that thing. This is the Finney DeMano Waits Kennedy book. You probably ought to take a look at the exploration on page 102 just to cement in your own mind what we mean by rates of change and how they look like derivatives, how derivatives really are rates of change. Okay, so those are the big ideas. Those are the big ideas. I want you to know what a derivative is. I want you to know how the definition looks. And I want you to be able to play the algebra game. Okay, so hey, one more thing before we're done. It could happen. It could happen where you're asked to do something like this. If the limit as h approaches 0 of f of 3 plus h minus f of 3 over h is 5, find f prime of 3. And then you would have to know, wait a second, this is the derivative of the f function at x equals 3. This is 5. It would come up early in the multiple choice section because it's a pretty quick question to do, but you want to be able to make connections. You want people to be able to say, if they throw this at you, find f prime of 4, you want to be able to say, I know what that is. Or if they say, find the equation of the tangent line, or they say, find, I don't know, I mean, you could throw it out in a whole bunch of different ways. You want to be able to make connections and say to yourself, I recognize this as the definition of derivative. We got to drive home. Okay, so that's our 15 minutes. When we come back tomorrow in class together, I'm going to show you some graphs and ask you where they're differentiable, where they're not differentiable. We're going to run through some highlights, and we're all set. Awesome. Thanks, everybody. We'll see you tomorrow.